Good morning to respected lecturer and fellow students. This presentation analyzes the lead-tin binary system, a well-known eutectic alloy widely used in engineering applications. The study focused on phase diagram, lever rule analysis, and sustainable production practices, demonstrating the application of phase equilibrium concepts in practical engineering contexts. The structure of this presentation is as follows. First, the introduction and objective of the study will be outlined. Following this, Task 1 will cover the phase diagram and engineering application of the PBSN system. Task 2 will present the lever rule analysis and calculation of phase fraction. Finally, Task 3 will examine the system's relevance to Sustainable Development Goal 12 before concluding the study's finding. Phase equilibrium is a fundamental concept in engineering chemistry, explaining the behavior of materials under varying conditions of temperature, pressure, and composition. In practice, most engineering materials are mixtures rather than pure substances, making the understanding of phase behavior critical for material design and process control. Binary system consisting of two chemical components provide a simplified yet effective method to study mixtures. The lead-tin system is a classic example of a eutectic alloy extensively used in soldering application due to its low melting point, good fluidity, and strong bonding with metallic surfaces. Analyzing these systems allows engineers to predict phase formation, control material properties, and ensure the reliability and efficiency of the engineered component. The objective of the study are fourfold. First, to analyze the PBSN phase diagram and identify the phases present under various composition and temperature. Second, to apply the lever rule to quantify the proportions of solid and liquid phases at a selected composition. Third, to evaluate the relevance of the PBSN alloys to Sustainable Development Goal 12, focusing on the material efficiency, energy consumption, and recyclability. Finally, to demonstrate the application of the theoretical phase equilibrium principle to practical engineering system, bridging the gap between the theory and real-world engineering practice.
In this section, I will explain the selection and analysis of the PBSN alloy system. First, let's look at the engineering application of the PBSN system. The lead-tin alloy is widely used in engineering, especially in electronics and electrical industries. It is commonly used as solder because it has a low melting temperature, good wettability, and reliable mechanical and electrical properties. Typical application includes printed circuit boards, electrical joints, plumbing, and metal joining. The eutectic composition, which is around 63 weight percent tin and 37 weight percent lead, is especially important because it melts and solidifies at a single temperature, allowing precise and defect-free soldering. Next is the justification for selecting the PBSN system. This system has a simple eutectic phase diagram, making it ideal for learning and analysis. It clearly shows eutectic reaction, phase transformation, and solid-liquid equilibrium behavior. In addition, PBSN alloys are widely used in real industries, which help theoretical phase diagram concept to practical engineering applications. Lastly, we consider the influence of temperature and pressure. Temperature plays a major role in phase behavior. As the alloy cools, it transforms from liquid to solid phases depending on its composition. At the eutectic temperature of about 180 degrees Celsius, the liquid transforms directly into alpha and beta phases. Pressure, however, has a negligible effect under normal engineering conditions, so the phase diagram is usually considered at constant atmospheric pressure. Now, let's move on to the PBSN phase diagram. This diagram shows temperature versus composition, with composition expressed in weight percent of tin. The key feature here is the eutectic point, located at approximately 63 weight percent tin and 180 degrees Celsius. Above the liquid lines, the alloy exists as a fully liquid phase. Between the liquid and solids line, we see liquid plus solid regions, either liquid plus alpha or liquid plus beta. Below the eutectic temperature, the alloy exists as a mixture of alpha and beta solid phases. Overall, this phase diagram helps us to understand how PBSN alloys solidify and why the eutectic composition is so important in soldering application.
For task 2, I will explain the level analysis for lead-tin or PBSN binary system. The level rule is a method used to determine the fraction of phases in the two-phase region of binary phase diagram. In this analysis, the overall composition of alloy is assumed to be 35 weight per tin and the temperature considered is 150 degrees Celsius. At this temperature, the alloy lies in the alpha plus beta region, where the alpha phase is lead-rich and the beta phase is tin-rich. Based on the PBSN phase diagram at 150 degrees Celsius, the composition of the alpha phase is approximately 10 weight per tin, while the beta phase contains approximately 98 weight per tin. Using the lever rule, the fraction of the alpha phase is calculated to be approximately 71.6% and the fraction of beta phase is approximately 28.4%. These results show that the alloy is dominated by the lead-rich alpha phase with a smaller proportion of the tin-rich beta phase. This phase distribution affects the mechanical and melting behavior of the PBSN alloy, which is important for engineering applications such as soldering. This concludes the level rule analysis for task 2. Thank you.
How does the application of lead-tin binary system supports SDG12? What is SDG12? It is responsible consumption and production. The lead-tin binary system is widely applied in soldering and alloy manufacturing, especially in electronics. Understanding its binary phase diagram supports SDG12 by enabling more efficient, safer, and sustainable material use. Firstly, the lead-tin phase diagram helps engineers select the optimum alloy composition, such as the eutectic composition, 63% tin, 37% lead that melts at a lower temperature. This reduces energy consumption during manufacturing, supporting responsible production. Secondly, proper use of the binary system minimizes material waste. By knowing solidification behavior and phase stability, manufacturers can avoid defects like incomplete melting or brittle joints, reducing rejected products and rework. Thirdly, knowledge of the lead-tin system supports recycling and reuse. During solder recovery from electronic waste, understanding phase relationships allow efficient separation and reprocessing of lead and tin, promoting circular economy practices. Lastly, applying binary system principles helps in the development of alternative alloys, encouraging reduced reliance on hazardous materials like lead, which aligns with environmentally responsible consumption. Overall, the lead-tin binary system contributes to SDG12 by improving resource efficiency, reducing waste, lowering energy use, and supporting sustainable materials management. In conclusion, the objectives of this study were successfully achieved through the analysis and results obtained. The lead-tin binary phase diagram was analyzed to identify the phases present at different compositions and temperatures. The lever rule was applied to determine phase fractions. Considering an overall alloy composition of 35 weight per tin at a temperature of 150 degrees Celsius, the alloy consists of approximately 71.6% alpha phase and 28.4% beta phase. This confirms the practicality of using the lever rule in predicting phase proportions in binary alloys. The study also showed the relevance of the lead-tin system to Sustainable Development Goal 12 by highlighting how proper alloy selection can reduce energy use, material waste, and recycling. Overall, this study demonstrated the practical application of phase diagram and lever rule concepts in engineering and sustainable manufacturing.